Hello, we are Team RoverOva from VSB Technical University of Ostrava, and this is our rover, K3P4. Our team was formed at the end of 2016, and since 2018 we have participated 4 times in the European Rover Challenge, winning a 3rd place in 2019 and a 2nd place in 2020. Currently, our team has 8 students, and we are preparing to compete in the first Anatolian Rover Challenge. We meet once a month for a week-long work sprint. The work is organized through a Kanban board, with each team member responsible for a subset of tasks. We design our rover in Clio Parametric with its product lifecycle management tool, Windchill, which allows all members to have the current 3D models and documentation. Our workshop is equipped with 3D printers, a pedestal drill, and handheld power tools. Therefore, to be able to produce parts in-house, the mechanical design is mostly focused on 3D printing or parts that do not require heavy machining. The rover's mobility system consists of an undercarriage with a rigid rocker suspension. The 4 wheels have integrated hub motors. These are 200-watt BLDC motors with planetary gearboxes. There are also 90-watt DC motors with planetary and worm gearboxes, which can steer the wheels individually, giving the rover the ability to drive using several configurations. We designed this suspension with rigidity in mind. Our 3D printed tires help the wheels get necessary traction and provide the rover with compliance to terrain. This, along with the rocker suspension, gives the rover good driving characteristics in terrain with relatively high maximum velocity. The mobility system, without additional modules, weighs 35 kilograms, can traverse 20 cm high obstacles and drive on an incline of up to 40 degrees. The electronics in the rover are divided into 2 circuits. One circuit powers all motors, and the second circuit powers the logic components. Each circuit is powered by a separate battery that can last up to 2 hours. Voltage, current, and power are monitored with measurements on display. An emergency stop button disconnects batteries from all electronics. At the heart of our rover is a Jetson Xavier NX computer, which communicates with various microcontrollers in additional modules through USB, UART, and I2C. Power distribution boards and driver boards are custom designed and allow us to fit all necessary electronics even in tight spaces. The rover is equipped with a 5 degrees of freedom manipulator that can reach the ground on 3 sides of the rover, which gives it versatility in terrain. The arm is capable of pressing buttons, operating switches, inserting plugs, opening drawers, turning knobs, and opening valves. The arm itself weighs 9 kilograms and can grasp and carry objects of various sizes, weighing up to 5 kilograms, or pull heavier objects. We have implemented 3 ways to control the manipulator: a direct teleoperation joystick that can be used to intuitively control the arm with one hand, automated mode that can drive the manipulator to safe positions, or we can switch to an inverse kinematics mode for precise control. We are in the process of building a new manipulator with 6 degrees of freedom and a custom 3D printed cycloidal gearboxes, which we have designed and tested. Science module is a fixed module with 5 separately detachable containers. The containers are always closed and open automatically, only for a short moment to allow pouring of the soil sample. Then it closes again and keeps the sample from contamination. The sample containers feature sensors to measure weight, temperature, humidity, color, and gas emissions. The soil samples will then be analyzed in a laboratory setting. The analysis focuses on detecting extinct life through tests for proteins and fats. The rover can be controlled with an 868 MHz RC transmitter or over Wi-Fi. If a signal from the RC transmitter is not available, the rover automatically switches to Wi-Fi. Video from IP cameras and webcams is transmitted over Wi-Fi. These cameras are high definition and capable of 4 times optical zoom. The Wi-Fi can, however, slow down the video transfer depending on the signal strength. That is why we have also implemented analog FPV cameras. The video from analog cameras is transmitted over 5.8 GHz band. Multiple analog FPV cameras with the video signal switch are used for low resolution but real-time feedback. With these systems, even if the rover loses Wi-Fi signal, we can still drive the rover with visual feedback, which allows us to finish missions even in environments without line-of-sight communication. The Wi-Fi and analog video have range of about 1 kilometer. The RC transmitter can control the rover to up to 10 kilometers. The cameras, along with real-time 3D visualization, provide good situational awareness for the rover operators. For navigation, we use a GPS module and a Z2 depth camera. Obstacle detection and avoidance is implemented with the help of RTAB map algorithm. The item detection uses ARC' visual tags for identifying various goal objects during the IRC missions. We also use ARC' detection to automatically drive the manipulator to target positions on the control panels. Building this rover was a great experience that taught us many engineering and managerial skills. But most importantly, we have had a lot of fun along the way. We are looking forward to meeting other teams at the Anatolian Rover Challenge.